CDMA3.2.CDMCDMA. The CDMA method is evaluated as a suitable technology for cellular networks in that it has high-frequency reuse efficiency, and it is a technology being discussed as a multiplexing multiple access method for IMD-2000, which is referred to as a future mobile communication technology. Here, we will talk about the CDMA system, which is a practical application example of the spread spectrum communication method. 3.2.1 Spread spectrum communication and conventional communication. The conventional method for ensuring the independence of each of several communication paths is the frequency division method, which constructs and transmits channels by splitting the entire frequency band into several frequency pieces. Here, a channel refers to the actual thing through which a call connection is established. On the other hand, it is also referred to as every call connection between a receiver and a transmitter. In the frequency division method, a channel refers to each divided frequency band to be distributed to users. Therefore, due to the characteristic of having different frequencies from other adjacent bands, relatively high independence is guaranteed. Meanwhile, since this method uses a narrowband compared to spread spectrum communication, which uses the entire band as a single channel, spread spectrum communication is called wideband communication, and conventional communication is called narrowband communication by comparison. In narrowband communication, the bandwidth of the baseband signal is modulated as it is into the RF radio frequency band, which is the radio frequency for transmission, and the RF modulated signal passes through a channel and is received by a receiver. The received signal contains the information signal and noise, and the quality of this signal is evaluated by SNR, which stands for signal-to-noise ratio. In the case of narrowband communication, the SNR of the demodulated signal is the same as the SNR of the RF band. This can be confirmed through Figure 3.2.2. Before considering the difference between narrowband and wideband communication, let us first consider the general process of communication. The very first thing done prior to digital communication is source coding. Source data to be transmitted, for example, a human voice or images and videos captured by a camera, is converted into an information signal. Converting into an information signal means mapping the degree of transformation of the source information to a certain frequency range of an electrical signal. Then, a baseband signal existing within a certain frequency band is created. The created baseband signal is then moved to the RF band to be carried on a carrier wave for transmission. At this time, the bandwidth of the information signal does not increase, but the center frequency of the bandwidth increases by the amount of the carrier frequency. Therefore, modulation occurs where the center frequency of the information signal, which appeared in a certain frequency range, moves to a much higher frequency. For example, a signal with a center frequency of 4 kHz and a bandwidth range of plus or minus 4 kHz is changed into a signal with a center frequency of 1 GHz and a bandwidth range of plus or minus 4 kHz. Of course, the process of making source information into a baseband signal is also called modulation. But in digital communication, the expression mapping seems more appropriate and is used more frequently. However, one thing to note here is that the RF modulation mentioned here is distinct from the spreading modulation that will be discussed later. On the other hand, in the case of CDMA, which transmits information signals through a wideband, the baseband signal is a wideband signal just like the RF band signal. To be more precise, the RF band becomes wideband because the baseband signal is spread into a wideband. Like conventional narrowband signals, noise is added to wideband signals as they pass through a channel. The noise added while passing through the channel can be understood as a jamming signal that interferes with communication using the same frequency band as the information signal. Of course, noise caused by thermal noise and the like added to the narrowband communication channel is also added here. If this channel represents the channel conditions of a mobile communication system, the jamming signal can be thought of as the signals from other terminals. Unlike narrowband, the SNR of the demodulated signal for a received wideband spread signal has a gain compared to the SNR of the RF signal, equal to the total bandwidth divided by the user bandwidth. In other words, there is a gain equal to the ratio of the spreading bandwidth to the information bandwidth. This is called the spreading processing gain because it is a gain obtained by spreading phi information. This can be confirmed through figure 323. As a result, even if a jamming signal that can become an interference signal is added to the transmitted band, it can be seen that when the information signal is spread and transmitted over a wideband, it possesses sufficient SNR for demodulation, due to the processing involved in spreading the signal over a wideband. However, the jamming signal mentioned here refers to another signal or transceiver using the same signal band. Since this is generally a situation where crosstalk occurs, it does not seem to align with common sense. For this reason, it is also called the paradox of spread spectrum communication. Narrowband communication forms channels by dividing the entire band by frequency, and secures channel capacity, based on how finely the frequency to be allocated to an individual within the entire band can be split. Compared to this, the wideband spread spectrum communication method forms channels by dividing the power of the entire band, and secures channel capacity, based on how finely the power to be allocated to an individual within the entire band can be split. That is, the two systems being compared differ in whether the factor distinguishing channels is frequency or power. Therefore, which factor we can improve or control more easily will serve as an indicator to determine which system is better for us. The capacity of spread spectrum communication, such as CDMA, is determined by the interference factors appearing in the channel. In other words, it is determined by how many interference factors exist, or how much those interference factors can be reduced. Therefore, technology that improves demodulation performance to allow for demodulation, even in poor SNR environments, becomes a method for increasing the capacity of this system. 3.2 Quantitative analysis of the CDMA communication method. Generally, in the spread spectrum communication method, codes that distinguish each user are used for multiple access. The output of the signal modulated by each code used is strictly limited, which is to maintain the allowable signal-to-noise ratio required by the system, namely EBN0, when operating with CDMA, multiple subscribers. In this case, a specific subscriber will receive a signal in the form of equation 3:1. Here, each signal appears at the receiving end with the same power PS, and each PN code used by the subscribers, GIT, is represented by the same chip rate FC. Also, the information data transmitted by an arbitrary user I is represented as DIT. Of course, the data transmission rate of each user's information data is the same as FB. Additionally, theta is a random phase that is independent of the respective phases of other users. Furthermore, thermal noise will be excluded from consideration to simplify the explanation. Now, let us consider the case where the first subscriber, where I is 1, receives the signal. First, to despread the received signal will be multiplied by the PN code signal G1 ton. Subsequently, the information data will be multiplied by the carrier signal cdma3.2.CDMCDMA, which is the carrier wave with a phase shifted by theta 1. That is, it will be multiplied by D1 ton cdma3.2.CDMCDMA. As a result, the signal demodulated by the receiver of the first subscriber is as shown in equation 322. That is, by multiplying by G1 ton, the spreading component is despread, and only D1 ton cdma3.2.CDMCDMA will appear. The created baseband signal is then carried on the carrier wave and moved to the RF band for transmission. Furthermore, the other PN codes multiplied by G1 ton still remain as shown in the right-hand term of equation 322. Here, if we define G1 ton, G as G, I1, ton, and cosine theta I as cosine theta, I1, equation 322 can be rewritten as equation 323. In equation 323, the right-hand term represents the signals of K-1 independent subscribers, which are the interference signals to the signal of the first subscriber. As in the case of the single-tone jamming signal obtained in the previous chapter, the interference generated in this case is a jamming signal caused by K-1 terminals, and thus it can be calculated as a value K-1 times larger than a single-tone jamming signal, when the average phase of the jamming signals is 45 circ. This is called effective jamming, and the total power spectral density of the interference signal at this time is as shown in equation 324. In addition, since all users other than the first one, the bit error probability Pj is k-1 times Ps. Therefore, it can be written as in equation 3 to 5. Consequently, to maintain a low error probability, the x value of the error function text, earth x, must be much larger than 1, that is, the condition must be as shown in equation 3 to 6. The performance of a CDMA system, which is a spread spectrum communication system, can have effective communication error performance only when the spreading processing gain is much larger than the number of subscribers, k-1. For example, if there are 100 users using voice source data of 8 kbps per person, the spreading frequency bandwidth, or the chip rate of the code used for spreading must be much larger than 0.8 mbps. If the number of users is reduced to 10 while the transmission band remains at 0.8 mbps, the processing gain of the information data is relatively increased, and as a result, the bit error probability will be significantly reduced. This means that the output power of each piece of information data can be further lowered. 3.2.3 Jamming margin equation. The anti-jamming performance of CDMA refers to the interference performance of the system, and the interference performance of the system is directly linked to the communication capacity of the system. Now, let us consider the jamming equation that can graphically represent the anti-jamming performance of CDMA. To derive the jamming equation for a CDMA system, we will set a few parameters as follows. When the received power of the information signal is S, the power of the unwanted jamming signal is J, the data transmission rate is R, the spreading bandwidth is W, the energy per received bit is E, B, and the power spectral density of noise is N0, the jamming margin equation can be expressed. That is, the jamming signal J can be represented as the product of the noise energy density function across the entire transmission band, and the energy of the signal can be obtained by dividing the energy per bit by the bit period. The signal-to-noise ratio obtained in this manner is expressed as in equation 3 to 7. In other words, the analysis of noise relative to the system's signal is expressed as the value obtained by subtracting EBN0, the signal-to-noise ratio per bit, that allows us to maintain the tolerable error probability from the processing gain. Furthermore, processing gain can be described as the resistance of the CDMA system against noise or jamming signals. That is, the larger the processing gain, the greater the margin against jamming, and the more the information data is spread, the greater the margin against jamming becomes. Early CDMA technology was developed for military communication technology where highly secret communication was required. This was due to the anti-jamming performance of the CDMA system. Figure 3 to 4 is a graphical representation of the anti-jamming performance obtained through the processing gain of spread spectrum communication. This is reminiscent of a situation where a signal source defends against the intrusion of a malicious noise signal when such a signal infiltrates the signal source's domain. The signal source on the left in figure 3 to 4 depicts the shape of equipotential lines representing its own sphere of influence against the impact of a jamming signal source transmitting identical power in the same band on the right. At this time, let us examine in what shape the distribution of power changes. When the positions of the signal source and the jamming signal source are represented by x and y coordinates, the coordinates of the signal source are 0, 0, and the coordinates of the jamming signal source are 200, 0. Assuming that the propagation space is free space, and that attenuation occurs according to Gauss's divergence theorem, the power distribution from either the information signal source or the jamming signal source is represented by 1 or 2. Furthermore, assuming that the magnitudes of the information signal and the jamming signal are equal, we can express the ratio of the received signal to the jamming signal, as in equation 3 to 8. Here, ρ is a value representing the magnitude of the jamming signal relative to the information signal. To draw the newly formed signal distribution curve based on this value, equation 3 to 9 can be rewritten as follows. That is, the radius and the center are expressed as functions of ρ. Let us consider a case where ρ 10. If we assume a scenario where the jamming signal is 10 times greater than the information signal, the resulting power line distribution will be in the shape of a circle centered at 222, 0, with a radius of 70. The anti-jamming performance of spread spectrum is explained in terms of call capacity in commercial communication networks. On the other hand, spread spectrum communication used in military applications is a capability that allows protection from jamming, such as security or electronic counter. The commercial communication to which spread spectrum CDMA is applied is the cellular mobile communication network we use. In the CDMA method, which is a form of spread spectrum communication, information is transmitted over a bandwidth sufficiently wider than the information data to secure channels, and channel capacity is secured through the spreading processing gain obtained from this. Along with this, there is power control as a measure to reduce interference conditions in the channel. Power control involves quickly and precisely adjusting the output power of the base station and terminals while a call is connected. Among the signals I receive, everything other than the signal I need to transmit and receive is an interference signal. Similarly, I must adjust my power so that my signal does not become interference to the communication channels of other terminals within the cell besides myself. This can be encountered in detail in Chapter 5 of this book. Another method to reduce unnecessary interference is cell sectorization technology, which adjusts the direction of interference using directional antennas. Furthermore, since the channel capacity of CDMA is not a fixed resource like FDMA, but rather a capacity that varies according to channel interference conditions, or follows a statistical distribution. Vocoders such as QCELP, which use variable bit rates, are used.